Hi, my name is Duncan. This is my OSDC-PIRE video teleconference presentation. I'm a first-year PhD student in computer science at UCLA. As you might know, the school has a rivalry with Kevin Creamy's school, USC. I work in the computer graphics lab with Professor Dimitri Terzopoulos. My project did not have anything to do with computer graphics, however. It dealt with detecting anomalous audio within audio streams. So a short example of why you might want to be able to do this is consider this automated car factory over here. There will be some background noise in this factory that changes over time. You would hear the sound of welding being done, the sound of motors turning, and cars clanking around. But if you heard a drastically different sound, like some robbers breaking in shouting, "We made it!" then you might want to dispatch the police automatically. So if this process can be done robustly, then you wouldn't need a security guard staring at a camera. You could just set up a computer with a microphone, and that would put that security guard out of work, and that's what we're trying to do here. So there's two main requirements for what we're working on. You must be able to adapt to changing background noise, because like the background noise in that factory is going to change with time. But we're going to assume it's not going to change that drastically with time. If it changes drastically with time, then it is anomalous. And the computer must be able to run on like a normal desktop computer and process the signal in real time. We can't have the analysis be lagging the incoming stream. So the technical approach we're going to use, so most machine learning approaches use simple features, complicated classifier. We're going to do the opposite. We're going to use a complex feature which is designed to work with audio signals called FLAC, Fourier local autocorrelation. And we're going to combine that with two different classification methods. The first we're going to try is called the subspace method. The second is the local outlier factor. So the Fourier local autocorrelation is pretty simple. There are 4 steps, and I think I need to read that aloud. So you just get these 2x2 masks, and here are the masks. You take a complex number from each mask, then you multiply it, then you get the feature. So we're going to do these 4 masks. And so for the subspace method, it's quite simple. You basically build a subspace using all the points you are known to be background sounds. So you build a little subspace using principal coordinate analysis, and that'll give you a nice little subspace. We can only take like the leading eigenvalues from that to get a small subspace, and then for every new point you just take the distance between that point and the subspace. And the idea is that if your distance is over a certain threshold, then you are anomalous. Otherwise you'll be added to the subspace, and that's how we can adapt to changing background sounds. So the other approach we tried was called local outlier factor. This is a more direct approach. You don't build a subspace, you just look at the points and compare them to other points. So specifically you look at the local density of a point, and points with lower local densities than neighboring points are outliers. So just to get a sense of how this works, here's a bunch of points, and here are their scores, their outlier scores. Like you notice, like this guy got a huge score because his local density is very small. Like there's nothing around him, but look at his closest points. Those guys have a lot of people around them. So that's the basic idea behind local outlier factor. It's very intuitive actually. So prior work on this topic, we had a paper come out about highlight detection, like when something interesting happens in an audio feed from a sporting event, but this was very specialized, and it did not work online. And then we had another paper specialized for detecting voice activity. So it used a slightly different kind of FLAC, which did not use complex numbers. So results, both of them are reasonable, but we didn't really get a chance to evaluate them that rigorously. Here's a brief demo. Unfortunately, I'm over 5 minutes, so I cannot show it to you, but it was cool. In future work, we want to classify different anomalies because, say, one anomalous sound in that factory setting might be a robot breaking in, but another might be a robot just messing up. And if a robot breaks or something, then you would want to alert a technician, not a cop. So that's why classification is necessary. Goodbye.